Now let's talk about equilibria that involve solids and or liquids. So the first thing we want to say is that solids do not appear in equilibrium constant expressions. If a solid does have a concentration, which I think is more of a philosophical question, it never changes. Liquids do not appear in equilibrium constant expressions either. A liquid in a reaction is the solvent. Solvents are assumed to be pure or nearly so. And so liquids do have concentrations, but they are constant, certainly over the reactions that we look at here. So those are our two rules. In fact, the only things that appear in equilibrium constant expressions are gases and aqueous phases. And don't worry, that leaves us plenty of stuff to do. Here's an example. It says Kp equals 1.04, and it says units there, but it shouldn't. 1.04 at 1100 Kelvin, because they are always in atmospheres, or we use atmospheres for our partial pressures for those. It says write the Kc and Kp expression for this reaction in which there are two solids. So let's write Kc first. Kc is going to equal concentration of products raised to the coefficients, which are just 1. The other two things are solids, so they do not appear, and done. Kp, partial pressure of carbon dioxide, others are solids, and done. So you can write a Kp expression as long as gases are the only things that appear in it, which is fine. So this is a valid Kp expression. And while we're here, let's find the relationship between Kp and Kc. We have that general relationship, Kp equals Kc times RT delta N, where delta N is moles of gas on the product side, 1, minus moles of gas on the reactant side, which is 0. So just to the first power. We can go ahead and plug in, we have Kp. Let's solve this the other way. Kc is Kp over RT in this particular case. And we have 1.04 over R Those are all my units. And our temperature in this case is 1100 Kelvin. And no, there's a calculator around here somewhere. 1.04 divided by 0.08206 divided by 1100. 0.0115 is our Kc value for this. Now let's do the same thing here. This time we have aqueous species, so we will not be able to write a Kp, but we will be able to write a Kc. Our products are both aqueous. And for our reactants, we have one aqueous species and one liquid. So liquids do not appear. And so this is our expression for Kc. Now, manipulating equilibrium constant expressions says, given the following reaction and its Kc value, we will eventually say, what is the Kc value for this? And remember, every reaction has its own Kc value. That's akin to when we were talking about the change in enthalpy of reaction, delta H reaction. So we said every reaction has its own delta H reaction value. And it will be true now how you get from one to the other. If you remember, for delta H reaction, if you flip the reaction, reactants becoming products and vice versa, you change the sign of delta H. This is different. So when you flip the reaction and the reactants and products here, well, let's take a look at it. Kc is going to be concentration of carbon monoxide squared over, well, we have a solid here, so just concentration of O2 there to the first power. For this reaction, since we've flipped things, our O2 is going to be on top. And just so you know, so I can keep my Kc's separated, I will call this one Kc1 in this case. I should do them in different colors. Kc1. There. And our denominator has CO squared. And so we can see that the relationship between Kc and Kc1 equals is a reciprocal relationship. So the phrase or the rule of thumb that we get is now flip the reaction take the reciprocal of the Kc value. And reciprocal just means 1 over Kc. You could also say invert, however you think it works for you. But that is something that comes up quite often, is taking the changing the reactants and products and taking the reciprocal of the Kc value. Now, let's see. Oh, so I should actually find this value. So if Kc was 2.1 times 10 to the 47th, then Kc1 is 1 over that. 2.1 exponent 47. It's a pretty large number, and equilibrium constants can be very large and correspondingly very small. So I took the reciprocal, I get 4.8 times 10 to the negative 48th power. Very good. That's better. Okay, so now the next question is going to be, what is the Kc value for this reaction? And you can see that what we've done is we have our original Kc. So now we'll call this Kc2. Kc, so what we've done is we've doubled all of our coefficients. And if this was delta H, when you double the coefficients, you double the delta H value. Here, so Kc2 will be the expression will be carbon monoxide concentration to the 4th power over oxygen concentration squared, which equals Kc squared. So here, double the coefficients, square the Kc value. And again, we will use this to do things like a la Hess's law that we've done before. Do you have anything else to say about that page? Nope. Now, new rule, if you add 2 or more reactions to obtain an overall reaction, multiply the corresponding equilibrium constants. And so here's an example. If we take carbon monoxide gas plus 3 hydrogen, and they're going to methane and H2O gas. And we have a Kc, or what we'll call Kc1, an equilibrium constant of 3.92, and I would have to give you this value. And then we have another reaction which takes methane plus 2 hydrosulfuric acid, hydrogen sulfide, it's in the gas phase, goes to CS2 plus 4 hydrogens. And again, we would be given this 3.3 times 10 to the 4th. We could add these two reactions, and we would multiply their Kc values. And just like Hess's law, anything that's on both sides, you can cross out. Let's see what else is on both sides. We have 3 hydrogens and 4 hydrogens, so we'll cross out all 3 of those and leave 1 on the product side. Our resulting reaction, let's see, carbon monoxide plus 2 hydrogen sulfide goes to carbon disulfide plus H2O gas plus 1 hydrogen. And what we'll call Kc3, so the equilibrium constant for this third reaction in red will equal Kc1 times Kc2. And the answer here would be 3.92 times 3.3 exponent 4. So I get 1.29 times 10 to the 5th. And actually, since I only have 2 sig figs here, I'd better go 1.3 times 10 to the 5th, although reporting to 3 sig figs is always fine. It's more proper in this case to do 2. In many equilibrium constants you will find we only have 2 sig figs anyway, so 2 will be fine. I think that's the last page for this video.